Okay, we're good. We're good recording. So welcome to today's session. This is Electronics 2 Cookies and Cram, and I've taken this session last year. We'll take it again today. I will share this document at the end of the session today, and it consists of all the important things we're going to cover. But to start off, we're going to look at identifying topologies. So one of the things that's very important in this course is just looking at a circuit and knowing what kind of amplifier you're dealing with, because a lot of times you have multiple transistors in them and not just one. So you have like multiple transistors, but if you can look at it and kind of see the input and the output of the different stages of your circuit that you're looking at, you're going to be able to identify, okay, this is a common emitter, this is common base, this is common source, blah, blah, blah. And I highly recommend you memorize the gains of all of these amplifiers. For example, if I ask you the gain of a common emitter, if you can tell that it's directly like uh, GMRD or something like that, it's going to save you so much time. Just write that there and then go on with your analysis. So this is just like a quick word of advice. Just go back to Electronics 1 notes, memorize all of the configurations. So one way to calculate gain in this class, as you guys have seen it already, is just AV, which is equal to minus GM R out, where GM is just the transconductance of your circuit. So you go to the output, you input a current here, you give an I output inside of the circuit, and you find the ratio, or you guys cannot see the laser now, can you? Okay. Okay, it's gonna be like that. Oh Lord. But here, pretty much, you give in I output inside, you find the ratio of I output to V input here when the output is grounded, and that's how you find your GM. And most of the time, the GM is the GM of the transistor that's connected to the input here. Not directly as a resistor, but you know what I mean. The signal goes through the base. And a couple of key points when doing that is when you're trying to find R out, this is basically Thevenin, so you want to disable all sources, AC and DC, everything. Once you do that, all of the transistors, you want to replace them with resistors. So you go to your cheat sheet, you find the corresponding circuit diagram you're looking at. For example, this is a transistor connected to the gate and then to the ground at one point, so you can replace it with a corresponding resistor. So you're going to do that. Once you convert all of your transistors to resistor, you can combine, and then you have R out. This is pretty simple. It's free grades right there. So if you can do that, I highly recommend spending a lot of time getting this right to maximize your grades. Usually, GM is the hard part, that harder thing to find. Because if you look over here, can I do this? No, I can't do that. Okay, no, okay. So when you're finding GM, you want to ground the output. So if I go back to the circuit that I have here, this output, you want to ground it. You want to connect it to ground. Once you do that, you want to provide I output into the circuit. So you're going to go from ground into the circuit. So if I was here, I'm going to ground my output, and then I'm going to give in I output into the circuit. So it's very important you get that configuration correct. Okay? Let's remove that. That's one thing. And you want to calculate the ratio of I out over V in once the output is grounded. Make sure all the DC, you can replace them with DC connector transistors, you can replace them with the resistors. So if I go over here, or let me look at this example. So if you were looking at something like this, so to speak, these ones you can ground, 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 but this one you have to leave it here. But these three, since they're connected to ground, you can replace all of them by resistors using the cheat sheet, except for this one. And who can tell me why you can't convert this one? Because you have a V and AC signal, so you can't convert this one. But once you convert all of those to resistors, you're going to have something like this. One, so you have a V in, a resistor, and your V out, which is grounded. So that's why you use Electronics 1 to find the I output over V input. That's why you use that. But approximate a lot as you do the, like use all the approximations possible when you're doing that. So any questions on these two? This is pretty straightforward, no? So let's move on to here. I'm not going to spend most of the time like just going through this because it's pretty easy stuff. We'll talk about feedback and stuff that's more important later. So how do we find R out? So if I want to try and find R out right here, what I want to do is I want to disable the DC. So these two are going to go to ground, and I have this going on here. And then you can do it any way you want, but I like to work from the ground up so I don't make any mistakes. So I go from the ground, I go up, I cross path with this transistor, and I check what terminals they're connected to ground to. Once I see that these two are connected to ground and this is connected to the rest of the circuit, I know I can look at it from the rest of the circuit and then replace this with a resistor that I called RM2. And RM2, I go to my cheat sheet, I find this kind of topology. I look at the equation of that topology, and then I replace it here. Okay, but in this case, you can see that you have RO2 and then GM2 and all that stuff. But from the cheat sheet, this you have an RS, right? In the cheat sheet, we'll see this connected to an RS right here. But in our case, this RS is 0, which is why this simplifies. So that's, again, pretty easy stuff. Once I have RM2 calculated from a transistor to a resistor, I have it there, RO2. So now I can find R out. So again, sometimes I just like to draw the small signal analysis, like the small signal model, not to solve it, but just so I can see things clearly. Because if you look at this one over here, you can see that there's something annoying with it. What's annoying about this diagram right here on the complete right? There's something about it that does not allow you to just transform resistors to transistors. There's something iffy that stops you from doing that. DRP, exactly. Because like, if you go to the cheat sheet, you won't have an RP attached. So then it makes it harder. And that's how he tries to trick you sometimes. So what I do is just like this MOSFET right there, I just replace it with a small signal model, and then I connect the RP. Because if you look at the RP is connected from the drain to the source. But coincidentally, it's parallel with RO1. All right, you guys see that? Like the RP is parallel to RO1. But in this diagram, you don't see that. But if you do it this way, you see it now. And once you see it, you can do that combination, and I can call it RO1 prime. So pretty much, I can ignore this RP that like even exists because it's part of RO1. It's like that early effect is just a modified version of itself. So then you can ignore it completely because you already take it into account here. And once you do that, your circuit just goes to this, which is available in the cheat sheet. However, you got to keep in mind that when you're using the circuit that's readily available to you in the cheat sheet, whenever you have RO1, you're using RO1 prime. Is that clear? Because we already did this thing, this parallel combination. So that's one thing to keep in mind. Whenever you get confused in this class, it's just one thing that always helped me is just draw the small signal model. Of course, not all for all of them. If you have a circuit, there's one transistor that's confusing you. Draw the small signal model, see what's going on. You don't have to do KVLs and KCLs. Just see what's going on. See if you can simplify and go back to the electronics 2 methods. It's like a ping pong between the two. And if you can do that, I think you're going to be very, very well set for this exam. So any questions on how I found R out here? And this is probably one of the harder R out examples with parasitic resistance, so that's why I thought I'd cover it here, so then there's no confusion. If you can understand this, I have no doubts you'll be able to do better, or other examples. And I always use the approximations. Do you guys know how to go from here to the approximation result, approximated result? GMRO is much greater than 1, so I can pretty much ignore the 1 here. That's what I did, okay? And then I have RO2 that's common, so I factor it out. But then I have GMRO prime plus R1 plus 1. But again, I use the same approximation and I get to here. This is pretty simple math. And it's just like from here to here, it's no big deal here. There's no circuits. So cascode amplifier gain. Do we know how to do this question? Any confusion? I'll just cover it quickly then. So what's the first thing you guys would do when solving this? Let's make it a little bit more interactive, so to speak. What's something that you would do? Yep, to find GM. Perfect. And what happens when you ground V out? Something happens. Boom, just like that. Boom, gone. So that takes me from here, exactly what you said. This is gone, so we're there now. And then what can we do once we're there? We can. Oh, there's one transistor connected to ground, one V in. What happens to the one connected to ground? What can we do about that? Can simplify it to a resistor. So that's what we do. And now that we have that, this is now readily available in the cheat sheet, and this is now grounded. So then you just go to electronics 1, V in, I out, you find that ratio. Are you guys confident in knowing how to find that ratio through electronics 1? Like, it's not that hard. It's just, I don't know, it's current, what do we call this again? Current divided? It's a current divided here, and then V pi 1 here, V pi 1 here, and then V pi 1 is exactly V in. So this is V in, and then you have the ratio of I out over V in. It's not that hard. So essentially, to summarize the step-by-step method, is you have this big thing going on. You want to find GM, you ground this. Once you ground this, this is disconnected. When this is disconnected, you have this transistor that's left. This transistor is connected to ground, so you can replace it. Once you can replace it, you have V in, I out, one resistor. Simple electronics 1 should take you 3 minutes to get the analysis done. And you can show that GM is equal to GM1. Or if you've done enough analysis, you can look at the circuit, you look at this, you're like, okay, GM is GM1, obviously. So that's how I got that. Sometimes I just never did this calculation. I just wrote the answer and I got the points for it for some reason. And then finding R out. Again, this is very explicit. Like it doesn't have to be this long. I just was very like, I went into excruciating details when I made these notes, so there's no ambiguity. But again, same step-by-step process. I like to work from the ground up and from the ground up. So when I do this, I'm going to replace this by its equivalent impedance. Same thing with here. This is RQ4, RQ3. I use the cheat sheet and I replace these two. So Q4 and Q1 are replaced. So that's how I got RO4 and RO1. That's one part of it done. Now I'm done with this one. I go down further and I go up further. Now I'm looking at this one and this one. However, I have to be careful that we have RO1 and then we have RO4. So when I'm looking at my cheat sheet, I want to make sure I account for those. And once I do, I'll have something like this. If this is a resistor right here, imagine a big resistor here. One, what kind of combination would that be? Looking at parallel combination. Perfect, perfect, perfect. Okay, beautiful. So then you just do this. You can leave your answer as that, or you can approximate. Actually, I recommend starting with the approximated solution right there, so you don't have to do all these things. So just when you're doing this, use, because on your cheat sheet you have the exact and the approximated, just straight up use the approximated. You're allowed to do that. And then it saves you time writing too. Like that's a lot of time writing parallels and all this shit. So okay, but you just can write it and then get that there. And then previously we said that GM equal to GM1. So GM equal GM1 times R out, and that's how you find the gain. Any question. It's just regular Cascode question here. Okay, it's differential amplifier. So you might have a question like this that's worth 10 marks. So you can review that. Differential amplifier, this question might be worth 10 to 15 marks. The French prof is pretty nice. He's gonna write in the question, use circuit splitting, so you know you have to split the circuit. Any questions on how circuit splitting works? Are we good to that? Are we good to that? Do you guys understand why we would use circuit splitting here? Because of the symmetry of the circuit? Okay, beautiful. Again, same step-by-step process. I feel like I'm repeating myself so much, but it is what it is. Ground, ground, ground. You get that. And because of the symmetry of the circuit, and these two are actually out of phase, like by 120 degrees, right? This is like phase shifted by 180, 120, 180. So when this one is increasing, this one is decreasing proportionally. So this point is always seeing an AC virtual ground. So you can treat this as virtual ground, only for AC though, not in DC. For AC, it's virtual ground. And once you have that, you can cut that circuit in half and only analyze one part of it. Again, I'm not gonna, we just calculated and showed that GM equals GM1 for this one in the previous question. It's the same thing. I'm not gonna write this down. You guys know how to do that. We're just gonna go straight to R out. Any questions on how to find R out here? It's not that complicated. It's the same thing as before. So minus GM R out, that's your gain. And this is how we solve the circuit. And I would recommend when you do something and you call it virtual ground, you can kind of draw it, do something like this. Do something like this. Say when this one increases, this one decreases proportionally. And then this sees an AC virtual ground. He loves that kind of stuff. And even if you do math mistakes, he's going to give you so much grade just for showing that. I promise you. Like try to explain that you understand these minor concepts, like transforming resistors to transistors to resistors, transforming this to a virtual ground. Like you know where it comes from and why you're doing what you're doing. Like if you can describe it in words even with no math, you will be rewarded for it. So that's Cascode. And then Miller multiplication for capacitors. This is when we get to the serious stuff. This is where things get a little bit heated. Do you guys understand Miller multiplication and Miller's theorem? Yep. So you understand why we have a minus sign here, if I were to ask that? Or why does this minus sign come from? Because I remember the slides there's a plus there. But when you're doing analysis, you always use a minus. That's a thinker of a question. It could be a multiple choice question, actually.
Was it a plus in the notes, you said?
There's a plus in the notes. Like if you open the notes, you could probably see a plus.
Really?
Yeah.
I always just gone off that formula.
I thought it was just the math that added up to be a plus.
It's actually quite simple. The minus sign here it conflicts with the notes for one reason. The notes uses impedance notation, and the impedance of a capacitor is what? Minus J over omega C. So that's where the minus sign comes from. So when you're using and in our circuits, we don't care about inductors, we don't care about nothing else that stores energy, just capacitors. So we're always using that. So always remember this one. CF is this one. So this capacitor is connected between two floating points, so V in and V out. So if you want to split it and have it connected to ground, you would use this equation where AV is the AC gain between the two nodes of the capacitor. Yeah? And do you guys know why we have to do that? Why we split the capacitors to have them connected to ground? Like, what does that simplify later on?
So we can add in other capacitors and then we find the poles.
Yeah, pretty much it. So then you can combine stuff like just like combine capacitors in general, and then see if they're parallel to a resistor. And the moment you have that, you have a pole. You can draw your Bode plots from the pole. And this is exactly the points where your your gain is gonna start to decrease.
Sorry, just a quick question.
Yeah, for sure.
In the notes, the general impedance is a minus, but for the capacitor, it says it's a plus. So like it says CF 1 plus AV, and then for general impedance, it's 1 minus. Like, is that like here it's minus for general impedance, and then for capacitor, he has like 1 plus.
Oh, but look at his gain. His gain is minus in the triangle.
Oh,
He's
okay.
yeah, he's like that. He's trying to confuse the hell out of you completely. His gain is minus. He's assuming that when you see plus A0, you're gonna read the triangle and take this minus A0 and put it inside of the A0. This guy, bro. I love him. Okay, well, finding poles is not that simple, but it can be super tedious. So step 1, disable all DC. Step 2, spot all capacitors. Step 3, deal with the capacitors connected to ground first, because you don't have to do anything to do with them. Step 4 is apply Miller's theorem for ungrounded capacitors. So like this one. That's when you do step 4. And then step 5 is all capacitors that are parallel to a resistor is going to produce a pole. When you're disabling sources, Vin is also disabled in pole identification, because if you look at the textbook, pole identification is derived from Thevenin. And what happens when you do Thevenin? You disable all sources, independent sources. Doesn't matter if it's AC or DC, it's the same thing. So, because if you look at the circuit here, you look at the AV, if I change this capacitor to this one and this one, this circuit here sees no change. So to this, whatever's going on here, this amplifier, no change has happened in the circuit, yet you know a change has happened. But it doesn't sense any change here. If you measure the voltage here and here, it's going to be the same. You measure the current flowing here, it's going to be the same. So it's derived from Thevenin. So you want to make sure that your input voltage is also disabled whenever you're doing pole identification. This is a very simple example. We have this common source amplifier. And this is why I said it's very important to memorize those gains of simple circuits. Because if you look at that and you know it's common source and you remember the gain, it's minus GMRD. And you know that AV is the gain between the V input and the V output, and when your capacity is right here. So in this case, again, this is your V output, this is your V input. So you could straight away go and replace your AV by the gain of the amplifier. You don't have to do analysis. But if you didn't know that, you'd have to apply KCL, KVL, and try to get that done and derive it. And that's going to take you like 5 to 10 minutes. So if you have it memorized, you can straight up go to it. But back to business, is this one is ungrounded. So I can pretty much bring it here when you have a CF1 and then you have a CF2. And CF1 is going to be given by what? This equation. And CF2 is going to be given by this equation, just following what we have here. Okay? And AV is, you have to be very careful. AV, in this case, is not going to be V out over V in. Why? Because AV is the gain at the nodes of the ends of the capacitors. So it's not this V in, it's going to be here, V1. And then this is going to be V2. But in this case, coincidentally, V2 is equal to V out. But we can't say that V in is equal to V1 here, because there's this device in the middle. So this is the gain that you're trying to find. And if you ignore this gain V2 or V1 is exactly minus GMRD. And that's how you have this gain. And then all you have to do is take this gain and plug it into your equation, and you have your capacitors. You have your capacitors CF1 and CF2. If you don't remember that the gain of the common, what is it again? If you don't remember that the gain of the common drain is minus GMRD, you can always do the analysis here. But I didn't do the analysis, but you can put it here and then you do the analysis. You will get minus GMRD and you have your capacitor CF1 and CF2 from there.
Okay. Not common source.
Common source. Oh yeah, that is common source. Why did I drag up? That's true, that's true, that's true.
No, you did write it. You did write it. You just looked at the thing below it. You wrote common source.
Yeah, no, but here I wrote common drain.
Oh.
I was wondering.
Yep. Common source. It's a good catch. Thank you. Okay. So now that we have our capacitance, this is good. Now what we can do is we can find GM and R out. Because you're still trying to find the gain, to be honest. Like you want to know the gain of the overall circuit. No, wait, what am I doing here? No. Okay, this is finding the gain, like minus GM RD. This is what I did. Like if you don't remember, this is how to get there. And I'm not going to cover that because that's too easy. It's right there, minus GM RD. Any questions on how to find that gain? No, this is pretty simple stuff. And all I did is I took that gain and I put it in AV here and AV here. And that's how I got my first capacitor value. That's how I got my second capacitor value. So my circuit simplified to this. But now, if you remember correctly, I said the V-in, you can disable it and connect it to ground. So then you will realize what is these two combinations. What kind of combination is that? Parallel, yeah? And these two is parallel as well. So you have two poles. I'm going to call this one the input pole because it's associated with input. I'm going to call that the output pole. You can call it whatever you want. Omega alpha, omega p, I don't care. It doesn't matter. I just called it that. And then you replace your CF1 by whatever value you have or CF2 by whatever value you computed. In fact, you can just leave it like this. If you've done this before, you already have this equation, you can leave it at this. You don't have to waste time to rewrite everything because it can get super long and you're just, wasting your own time there. But it's up to you, personal preference. So questions on how we found the poles? Is this, yes?
Okay, so I've seen like the conflicting things on the notes and
Yeah.
like assignments. When you take the pole, it's 1 over R times CF. Do you just take the resistor that's like parallel with the capacitor, or do you have to find R equivalent seen from that capacitor? Because like in some of the assignment solutions, they don't just take what's in parallel with like CF2, but they actually calculate R equivalent seen from CF2 and take that through the resistance. And online, like I've read before, you have to do R seen from the capacitor and not just what's in parallel.
It is R equivalent. But the reason why it's easy here is because if you look to the right of like CF1, it sees infinite.
Yeah, but like CF2, for instance, it wouldn't just be RD, right?
It would end up being.
Yeah, it would.
It would end up
Like
being
the
RD.
math, the math goes to that, but you do have to find R equivalent.
It is,
at that
you're
point.
right, completely correct. It is R equivalent as seen from the capacitor, but in fucking 90% of cases, it just ends up being the one that's parallel. Like if you do the math, you'll get there.
And typically when we do frequency response, do we neglect R or not?
Frequency response, I do. I always neglect it, unless it says otherwise. Okay, yeah.
So if you neglect channel modulation, if
Right.
lambda is 0, from CF2, the MOSFET would be of infinite impedance. But if you have like lambda not equal 0, would it just be RD in parallel with RL1 and R0 1?
Yeah. I think it would be.
It would be.
Yeah.
It would be, yes. So questions here?
I have a question
Yes, sir.
for all. So we know that he likes to add like little resistors everywhere in the circuit. So when you did it last year, did he like try and add them to mess up the gain, or did he try and add them to add more poles and zeros?
Oh,
If you remember.
he was nice.
Okay.
He was very nice.
It's probably the French prof's question.
Yeah, he was very nice last year. Like in terms of, there were no crazy resistors added. The only part that wasn't nice is his multiple choice.
Okay.
That's what I remember. Like his multiple choice was horrible. Yes.
Do you have any zeros? Because if you're using full identification.
Oh, you don't care about zeros in this class. This the only thing you care about is pole.
Did he ever ask for the transfer function?
No, God no. Like if he does ask it, it's not gonna be through AC analysis.
Yeah.
It's just through here. Like this is easy to get, you know.
Yeah.
Transfer function. Oh my God. Like I don't even know if I can do like. It's just
It would be long.
that I think just scares me. But there's that part.
By the way, I just wanted to say something. When I once talked to Momo during his office hours, and when we're doing like the approximations for Miller's theorem for the gain,
Yeah.
he said that sometimes it's better to not take the DC analysis, but a really high frequency analysis that like to do your AV. So if you have like a degeneration resistance anti-emitter and there's like a capacitor, disabling the DC sources, you do like your AV at a really high frequency, you bypass that resistance, and that's he said like he will accept it, and sometimes it's a better approximation. So like, if you're doing a frequency response and you need to like find your AV between the points, see like if it's better with DC or AC at
Yeah.
really high frequency.
I've always done AC myself. Like I've never considered DC.
No,
Like
but,
always AC.
Like for AV, when you like disable all DC sources at the very first, like for your Miller's theorem is what I mean.
Oh, here?
Yeah, yeah. Yeah. Like he said like for instance, like if M1 here
Mm-hmm.
had it like resistance.
Oh, I see what you mean now.
And then like as
I see what you mean.
He said like just assume we're like super high AC and not and you can just like use that approximation for your AV.
Okay.
So if you were to do like I forgot the name, a BJT, and you had like that, or you, like with the MOSFET, it would make the analysis much easier.
Mm-hmm.
Would you start gaining like intrinsic capacitance though? Like a really high frequency?
I
No,
think
but I'm saying like if you have like
it's a good question.
a resistor here at M1, and then you have a bypass capacitor, if you just write down like, I'm gonna do my Miller's theorem approximation at a really high frequency, thus your resistor goes to ground, and then you don't have to do Miller's on C mu or C pi, that one goes to ground, and then you have another one at ground already.
Yeah. It's a good point. So there's that. And then so this is like just a this was an example ignoring intrinsic capacitances of the MOSFET and the BJT. And then we're gonna do an example of intrinsic capacitance, like considering that too. But I don't think there are external capacitances in this circuit, it's just intrinsic. So we're gonna do that example, but this is a pretty mouthful example, so I think we'll take like a 5-minute break before we get back to this so we can look at it fresh.
Do
Like
you have an example where you have a resistance to use for Miller's theorem?
resistance to use for
Because usually, a lot of the times in our assignments, so, well, I think you did one example where you have a resistor instead of a capacitor. It's the same thing. Like
It's the
you
same thing, but I
apply
think it's just the
volts.
minus sign changes.
But for me, it's more like if you consider internal capacitance with the resistor, are you putting the resistor in series with the capacitor for Miller's? Or
Parallel.
Or yeah, sorry, parallel.
Yeah.
Okay. So you have to do like both, like two Miller's theorems?
Yes, you would have to do
Okay,
two of them. Yeah, yeah. You would have to do
Yeah,
two of
that's
them.
long.
Yeah, it's gonna be long. I don't think he's gonna ask something like that. Maybe for the assignment, yes, but not for a final.
Yeah,
paper.
sure. That's what it was.
Not for a final. So I put a timer.
And you have your
The questions on chat here.
When you're finding your Miller's theorem gain, are you shorting the coupling capacitor?
What?
Like if you have a coupling capacitor in your circuit, like not part of the intrinsic
Yeah.
capacitances, when you're finding your Miller's theorem across like your intrinsic
Yeah,
capacitances,
short,
do you short or do you open your coupling capacitor?
I think you short it.
Then you do short it.
What was the question?
If you have a coupling capacitor in your circuit, so a capacitor that's not part of your intrinsic capacitances, when you're finding Miller's theorem across your intrinsic capacitors, are you shorting or open circuiting that that coupling capacitor?
You short it.
Okay, that makes
Yeah,
sense.
because if you assume very high frequency that he said, the capacitor goes to short circuit. Yeah, it has to be shorted. Yeah. Yeah. Put a timer. Yes, this is we're gonna do this example. I think I remember last year when I did the cookies and craft for this session, I went through what was it? I think I went through this example. This is exactly what came out on the final. Like this is what they had last year. So I don't know if he'll be nice and give you the same thing, but if he's not nice, he'll give you something like this. But so we have it covered anyways. So we're gonna get through that one in 5 minutes, and then it's not bad.
It's just long.
It's just long. It's not bad to be
But
honest.
that question's worth 30 marks or 20 marks?
Probably 20. Probably 20.
Just that one.
Yeah, yeah. Just because of how long it is.
Would he give you one with capacitors, and then you also have to add the intrinsic one?
I don't remember having to do something like that. But even if he does, he's gonna have to be nice and like add them in a way where you can actually simplify. So
Also for
yeah.
feedback. I heard like the feedback question he gives are like fucked. There's like a 3-stage like fucking 3 parallel MOSFETs or something.
yeah, he's giving that for the past 3 years now.
Yeah.
Yeah.
Is it the same questions usually, or no?
Pretty much, yeah. But don't worry, like I have the exact same question.
Do you
I
have
think,
any
uh,
past finals?
I don't have past finals, no.
Okay.
But wait, is feedback? Okay, this is a feedback question that I have. But wait, hold on.
I just remember
On
taking
Discord.
the French exam last year, and you could see a clear difference between like his questions and
Yeah.
the French prof's questions.
My iPad's speaking. It's not working.
Yeah, he got like super he got like super ill. That's horrible. I felt bad.
I'm on like 60 HP right now.
Yeah. he's like
Someone
nerfed.
won't bump them, bro.
Everyone had a headache after some part. When you go through that many multiple choice, my head was
And it was all coding.
No, it's not the coding. It's like 75 multiple choice. You're like,
Yes, but like you have to like read the code and like analyze.
Mark Warren, respect your exam, bro.
Yeah,
Are you guys staying on campus?
staying till late.
Are you still studying email or not?
Yes.
I'm gonna be done. I've been studying email for the last 2 days.
oh, I look at that.
You had nothing to do.
Anything mind running me through like straight questions?
Sure, they're not hard.
Hey, this is what we're talking about.
Yeah.
Yeah, I have the solution.
What the fuck?
Just like, don't expose me. Expose me. I have it.
I do this recording and post it online.
This will be posted on. This will be posted. I'll play with fire, man.
But exclusive like for us.
No, yeah, but it's not. Yeah, I'm a shit. I'm gonna share it with people here, and then you can share it with the people you trust. That's how it works. But this is
It looks like I'm almost.
my name is not on there. I will.
Right, Rob, go wrong.
I'm just gonna do this.
But we in Trembling sounds better.
Okay, I can't
You
erase.
can't get in trouble for that.
That's crazy. I can't erase.
You can't even read.
Where's the feedback?
No evidence.
There's so much to look at.
This is wrong. Okay, it's not wrong, but it's wrong.
So fried because I went through the whole textbook. Every lecture slide, I didn't see anything close to this.
Yeah,
There wasn't one example.
I can run through it at the end.
Sure.
I will do that
That works.
because this is what's been going on.
That's the hardest part.
What the fuck
This
is
is a
that?
5-page solution.
Yeah, that's why it's like 30%. That's why it's like 30%.
Oh, I
Oh,
thought-
feedback.
That's a feedback question.
Oh, I thought frequency response.
No. Frequency response is chill. Feedback, yo. Feedback
Is it non-ideal?
No, the thing is, he tells you to do it ideal. No, not ideal. And then he tells you to do it non-ideal. And then he's trying to tell you if, can you take the limit as non-ideal goes to ideal? Like some momo, yeah.
Some momo
Some momo, like, yeah.
This is conceptual.
Yeah.
Maybe-
Okay, we'll do that later. Okay.
Very easy. Very easy.
So this guy was giving us like a pep talk in class and just saying if you understand everything, you'll be fine.
If you do the practice problem, that's the minimum requirement for this class. Okay, bro.
It's always like that. It's like, yo. Huh?
That's how we done that in your lecture where
Stop the class mid-class and just stares at us for 5 minutes straight, like nothing. Like no words. Just-
Really?
Yeah.
I feel like he.
and he'll stop to drink his water and then he'll just look back to stare at them.
And sometimes take us his handkerchief and it's just like,
He doesn't have a handkerchief for us.
He did last year.
oh, okay. Yeah, he's just gonna be like, CGD1 is connected to the gate, connected to the drain. Use Miller's identification to replace the capacitors connected to ground. Why? For half bonus mark.
Yes.
3, 2, 1.
Individually?
I will check the bar. Check. Let's get back to business, and I hope no one flames this point in the video. Sure. So we have this thing. These are the two diagrams. So this is for BJTs for MOSFET, the intrinsic capacitance. They call it weird names. They're just capacitors. This one is going to have intrinsic capacitances. This one's going to have intrinsic capacitances. So we're going to disable DC and VIN. So boom, boom, gone. Okay. And now I just draw all the intrinsic capacitances. For MOSFET 2, I'm going to have a subscript 2. For MOSFET 1, I'm going to have a subscript 1. And then you can look at this already and you can combine a lot of stuff. To start off with, these two can be combined. This capacitor is shorted. It's just boom, gone out of the picture.
Why are you grounding VN? Isn't that
Thevenin. Thevenin, because pole identification is derived from Thevenin. Yeah, good question. Very good question. Could be a multiple choice question. That's how he is. That could be a multiple choice question. Yeah. So I started combining stuff. I call it cleaning up. I started combining some stuff. And then the green is like what I'm starting to do. Now I'm starting to do the Miller stuff. So CGD1, I'm going to try to find CM1A and then CM1B to just get rid of that. And this is the equation. This is the equation for CM1A. And it's the equation for CM1B, where AV1 is VB over VA. So this is like the capacitor here. This is the voltage at the two points. So I just need to find that ratio. And if you look at this circuit, the MOSFET, you kind of have your output being VB and your input being VA, and that's a common source MOSFET, and the gain for that is minus GMR out, like, or you can just calculate the gain itself. I think this is what I did here. What did I do? What is that? Okay. RL. Ooh, hold on, I might need a minute to look at this for a sec. Out. CGD1, CM1A. Our out is there. Okay, I see. So this is where what you were talking about. Remember you said it's R equivalent as seen from the capacitance?
Yeah.
So in this case, this is where it applies. I kind of got caught up myself here. Because when you're trying to find the gain VB over VA, all this is like an impedance seen from that capacitor as well. So you need to consider it. And in this case, you actually need to, because the capacitor is connected right here, and you're trying to find that ratio of V1 over V2 over V1. Now, if you try to replace this, because if you look over here, you have MOSFET and then you have RL. Forget the capacitors for a sec. If you try to replace this with a resistor, it's not available in the cheat sheet. You can't go to the cheat sheet and find this topology and just replace it here. It's not available. So you're just going to have to use electronics 1 method. And what does that mean? It just means that you're going to have to find the equivalent impedance of this circuit. So if you draw the MOSFET, small signal model, you have gate, source, drain. The gate is connected to ground. This is the gate, right? And then the drain is connected to RL here. And the source is connected to your whatever input voltage you're given, VThevenin, because you're trying to find the equivalent impedance. Does that make sense? Like you put VThevenin with 1 ampere, you find VThevenin, you find your equivalent impedance. Sorry. So if you do this analysis, you're going to get VT. And VT is equal to your equivalent impedance. So any doubts on why I did what I did here? Because if you go back here, again, I'll zoom here. If you go back here, you have capacitor connected between VA and VB. You need to find the ratio of VA and VB. This you don't care because VA starts here. But VB is associated with this part of the circuit, so you have to consider it. Okay, as seen from this capacitor, you want to find the equivalent impedance. And when you're doing that, you have to replace this part with this equivalent impedance, but it's not readily available in the cheat sheet, so you have to do it yourself. You replace this by the small signal model. you give in at RM2. So at this point, you're going to give in Thevenin voltage with 1 ampere current. You find that VT, and then when you find that VT, that's your equivalent impedance that you can replace this by. And because this is MOSFET 2, I call it RM2. Yeah? Okay. And it happens to be 1 over GM2 from the analysis. So this is what you have here now. Now it's pretty easy to find R out. Again, I use the electronics 1 method to find R out. I just give in like V Thevenin right here into the circuit, and then 1 ampere of current. And I just ground my V input because I'm trying to find R out. And then this is ground, so this goes to 0. GMVGS goes to 0 because this is 0, so this is gone. My circuit is just this highlighted box. And VT is equal to 1 times 1 over GM1. So my R out is 1 over, this is GM2, sorry. My R out is 1 over GM2. And if you try to find the GM of the circuit, as I've said before, the GM of your circuit is almost always equal to the GM of your transistor that's connected to the V input. And in this case, this is MOSFET 1, so it's going to be GM1. So that means your AV is going to be minus GM times R out. R out is 1 over GM2, and GM is GM1, so it's minus GM1 over GM2. And that's your small signal gain as seen from the capacitors, considering the big jargon that went up on top of it. This is one of the examples where you have to consider the entire circuit. Okay, and that example is going to be posted so you guys can study it at your own pace. And once I find this gain, these equations that I wrote right here, 1, 2, the AV1 and AV1, I can simply replace by this GM minus GM1 over GM2. I put it here, and then I have my capacitors. So what does that mean? That means I can ignore this, and I can focus on the green capacitors I have there. And so that's what I did. I have this. And now you can combine stuff pretty easily because you have this one and this one that are in parallel. You add them. This one and this one, which are in parallel, so you add them. And your circuit becomes like this. Oh, okay. What did I do here? I see. So when you do this plus this plus this, that's 3 capacitors. But then this point is common between these 2 capacitors, and this point is ground, but this is also ground. So this is also parallel. So it's 1, 2, 3, 4. Clear? So that's all it is. I just didn't see it at first because I'm a dumbass, but here I saw it the second time I drew it. So I just drew it here. So this is combination right here. And then this is the combination of the input capacitors, and it's the combination of the ones at the output there. So looking at this, you can already spot 2 poles. This is 1, this is 2. Associated with the input, I'm going to call it pole input. Associated with the output, I'm going to call it pole output. Yeah? So, and then what is this parallel to? Parallel to what in question mark? So to reveal that, we're just going to go down here. It's parallel to the equivalent impedance R seen from here. So the capacitor is here. It has to be parallel to something that's connected to ground. But that something is the entire circuit without the capacitor, as seen from the capacitor, I should say. So you need to find the equivalent impedance of this entire circuit, as if you're finding RL in that first question we did. That's exactly what you need to do again. But again, it can be very harsh and give you a topology that's not readily available in the cheat sheet. So you have to go to electronics 1 method. Because if you look over here, R, this is what you're trying to find, because this is what's parallel with the capacitor that's going to give you the pole that you want. RM2, which is this part of the circuit, you already know it's 1 over GM2. But RM1, you don't know. Why don't you know that? Because there's an RS here, and in the cheat sheet, there's no RS at the gate.
Couldn't you just prove that because there's 0 current going through the gate, so then it would be short-circuited, and then...
Yep. You do that, and then that's it.
And just go back
Yeah.
to the cheat sheet.
So you can say that, or you can prove it. I did it here. 1 equals to 0, that's impossible, so RM1 goes to infinity. And that just means that you have R, which is parallel to RM1 and RM2, but one of them is RM1 goes to infinity, so your R is just this. So this capacitor here, this nasty one, is just parallel to 1 over GM2. That's all it is. And that's your middle pole, kind of in the middle here that I have here. And so this is how you find the 3 poles in this example. This is input pole, this is output pole, and then, I don't know why we call this one, omega P, I guess.
And that was when lambda is equal to 0.
And so no early channel modulation, yeah.
So
Yeah.
that's where M1 seen from R.
Yeah,
to
yeah.
infinity. If it wasn't 0, you'd see R naught.
You would see R naught one, yeah. because almost always when you have a GM, it's associated with an RO most of the time. But in this case, we're ignoring all the channel modulation stuff. So this is how we find the pulse. And I think this is where my YouTube videos ended. And I didn't cover more of the stuff. But this is transfer function. Once you find the pulse, it's pretty easy to find the transfer function. This A0, that's your regular circuit gain with no capacitors at all. If your capacitors, if your circuit did not have any intrinsic capacitors or outside capacitors connected to it, what would the gain of that circuit be? The answer is A0, just a regular gain. And omega pi, so 1, 2, 3, up until n, those are the poles that you have calculated. So your denominator is just going to stop at the number of poles that you have in your circuit. In this case, how many poles do we have? 3 poles. So your equation is going to stop till here, where omega 1, omega p2, omega 3 are just your omega p input, omega p output, and omega p. So all you need to do is, what is that? Computing A0. Okay. All you need to do is take those values here. So 1, 2, and 3, and then you replace it in here. 1, 2, and 3. Because you have 3 poles, it stops here. That's your denominator. Your only job is finding A0. And finding A0 is not that hard because it's just the regular circuit gain that you've been doing since the beginning of the class. So ignore all capacitors. You find minus GMR out. A0 is just minus GMR out. Again, disable all DC. You know how to find GM is I out over VN given the input, blah, blah, blah. You know how to do this. And then find the R out. We said this was infinity. So, hang on, what did I do? Okay, RM2, RS. Okay, in the cheat sheet, this is RS, but we know that this is infinity because we proved it earlier. So RM2 is equal to infinity. So infinite resistance can be modeled by an open circuit. So then your circuit just becomes like this because that's the only resistor you have there. And so R out is going to be equal to RL. So your gain is minus GM1 RL. Any questions on how I found the gain of the circuit with no capacitors? Usually when you have a frequency response question and he's telling you to find the transfer functions, the bulk of the question is, can you find the pulse? Can you use Miller's theorem? Can you find the pulse? Can you combine the capacitors? Do you know how it works? Do you know if you can you find the equivalent impedance of the circuit as seen from the capacitor? That's another thing. One more thing he's trying to see, do you know how to write the transfer function? So do you understand how you can replace your pulse by the equations that you received? One thing that he doesn't need to see that much is A0. Do you know how to calculate that? Because you already passed the midterm technically and you know how to do minus GMR out. So usually what ends up happening is there's a trick. This should be super easy. You shouldn't take your analysis super long. Either resistance is infinite, half the circuit is going to get short-circuited, so watch out for a trick there. Watch out that this must be super easy to find. If you find it hard, think about a trick. There could be something there that could make everything so much simpler. And in this case, that trick is just that this equivalent impedance is an open circuit because the resistance is infinite. And so all of this disappeared, and the only thing that's left here is RL. So your gain is going to be minus GMR out. GM is GM1, and R out is RL. So that's my gain. And now if I write my transfer function, it's going to be minus GMRL, which is A0. I stop at 3, 1 plus S over omega P in. Omega P in is this equation. I just didn't bother writing it again here because it's going to be nasty. Omega P is this one, and omega P out is this one. And this is actually, I think, an example from the lecture notes, but he doesn't post the actual step-by-step on how he gets there. So you can cross-compare and then see how we got this one. Now, once you find the transfer function, he's going to ask you to find the Bode plot. And to find a Bode plot, you just need to take the magnitude of this thing, boom, boom, and you take 20 log of that magnitude. Pretty much just like circuit theory 2 and signals and systems. So this is your equation here. It's not that hard. The only thing that I would say is you need to make sure you're plotting your poles correctly, and you need to show him that you know that your your gain is decreasing by 20 decibels per decade after each pole. So, and you want to label that this is frequency omega. this is your initial gain. So this is your steady state gain, if I were to give it that name. That's what this is. And then in this case, I don't know which pole happens first, which pole happens last, or where the poles are placed on the frequency axis, because we're not given numerical values. In your exam, you will be given numerical values, so you can plug in there, and then you have values for these ones, so you would know which one happened first. All I know is there's three of them, and they probably won't happen at the same time, so I have 1, 2, 3, and after each one of them, my gain will decrease, so that's how you draw the Bode plot. That's pretty much it. If you draw a Bode plot where you have something like that, you did something wrong. It can go up. In this class, you always go down. There's no zeros. So this will be clearer when having numerical values, but this is the main idea behind the poles. That's what I wrote here. So this is the huge feedback question, probably one of the hardest ones, because it takes so long and it's easy to make a mistake. So there's this one. Any questions about this example? Yes, sir.
Okay, so can you go to the when you found the gain between A and B? So it was up further, not the DC gain, but like for your Miller.
Oh, Miller. Oh, this one?
Yeah. So this might be a little stupid, but why can't we just for VB over VA? Why can't we just use the common drain or common source equation instead of doing that analysis? Like, isn't
But this is, you have a resistor there.
on top?
That's all a resistor.
Just since we have resistor, we can't use that equation.
Yeah. You have something like this. What the? Oh my! Yo, nothing wants to work today. You have this. You have this. This is the input. And then the resistor, like RL and M1, I'm just gonna call it R. And then this is the circuit.
Yeah. Yeah, I didn't know that.
But sorry, this is VB. This is VA. Do you see that? Like, this is connected to ground. Like, this point is like when you're measuring this with respect to ground, and this is with respect to ground. So it's kind of like this resistor is right here, and this is your output. Just like electronics one, this is your output, and you have R inside here.
Oh right, yeah.
So you have to. It's part of your gain.
Yeah, makes sense. Yeah.
That's actually a very good point. That's a good catch. But this is the reason.
Okay.
This is the reason. Because if you ignore it, you're doing this. There's that. Move that. Boom. Okay. Take one more 5-minute break, freshen up the brain before we go to feedback, which is the last thing on today's agenda. And then after this feedback is this to kind of increase, like, to help with the intuition of feedback. And then after this one, I'll go through the wrong solution. So
Do you have power as well?
power amplifiers, not really, because all it was on my exam, it was just a graph.
Okay.
Yeah, so I
It's
didn't
not that
think about bathroom break,
I thought
cookie
you
time.
would want, like-
Actually, I'm gonna have a cookie too.
I thought you would ask you like, what's the average power?
No, I don't think so. It could be multiple choice, so like this guy. On the multiple choice, I think I got like 2 marks out of 10. So
Is that bad?
at least don't do negative grades though.
Yeah. Imagine.
Well, it always comes up 5%, right? So
Yeah.
I took a VLSI with Imagad.
Oh, he puts negative.
Yeah,
Yes.
it puts negative grades.
really,
Yeah, I thought I would fail the exam, but not only just fail, I thought I would fail with a negative grade.
well,
That's insane.
do you think that course is tough?
No, I was just lazy.
No.
I could have studied, I didn't.
Negative grade is crazy.
It's like computer architecture 1, but with transistors.
Oh.
You already took it, you said, like last winter.
Yeah.
Or-
Transistors.
Like you build a whole multiplexer with the transistors.
I heard that the final project was like a full adder with MOSFET.
Yep.
That's not bad. That's kind of
You're taking random signals next semester?
Yeah. Wow. We have co-op, but
The prof is different this time though. It's Martin Bouchard. He was a French prof for signals, and apparently he's good.
Mm-hmm. I took it with Momo.
How was it?
oh,
Winter term.
Oh, he teaches randoms in summer. He teaches both the randoms and counts.
my God. You can just imagine having a math course with Momo.
What's Momo's best course? Like,
Is there a best?
Is there even
like, which course is he the best at? Because I've heard electronics isn't his.
Random signals, I think it was good.
Okay.
Yeah, I think he likes math a lot. He's a communication systems prof. Like, he loves Fourier. He loves that. I remember the French guys, they had no idea what was going on in their classes, but they were taking random signals. And then they showed up on the exam. There was a question they'd never studied in their life. Like, a whole content never covered it. And Momo was in our lecture. It was like, so today I will introduce the two-dimensional Fourier transform of the joint PDF. I heard that, I was freaking out. I was like, yo, what you mean two-dimensional Fourier transform? As if one wasn't enough, bro. And what he does in the next lecture is like, I prepared this document. It's very well written in LaTeX. It generalizes from 2 dimensions to n dimensions. So I have integral 1, integral 2, dot, 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 integral n. And he gives an assignment on it. that class, the average was bad. I think you can check it on you over it. It was like this curve.
it's like a roll up.
Freaking.
Went down by
It
it went down by
Negative
40
3D.
decibels per decade.
It had a 0. I think he does that on purpose. I think he knows. He knows. He knows.
Yes.
I hope everything going on well in his life. Like, and he's not taking it out on us, because
I don't think he likes you, Ottawa. I think that's his thing. He always has a Carlton, Carlton water bottle, and on his like LinkedIn, it's like Carlton.
Oh, okay, it could be something like that. It could honestly be something like that. I can't be one to speak though, because I'm gonna get in trouble if I open my mouth, so I'm holding my tongue.
I think we can say anything.
Yep. Do I remember how feedback works? Yes, a little bit.
You had Leica?
Just gonna ask.
I skip Loika, bro.
Yeah, I'm trying. My buddy had just his final.
Yesterday, right?
Yesterday. So have you heard about it?
Yes.
Yeah.
He asked a question on lab 3.
Yeah.
He gave a multiplexer question.
The last question was on the textbook. It was like not on the textbook. Like, what is the name of the textbook? What color was the front cover of the textbook?
That was the question?
Yeah.
That was the question.
That was the
Yo.
There was a 5-part question on different. It was like, what was the publishing date of the textbook? What was the name of the author? What was the title? What was the?
That's
color
not
of the
even
textbook?
allowed.
And my buddy's like, I had a black and white PDF. I don't fucking know what color the textbook.
Is that what he wrote? Did you write that? I had a black and white PDF. Yo, my friend deferred it. He just said that as deferred it. He's like, no, I'm not doing that.
Boyka doesn't write the
This guy's a
Yeah.
deviant. He actually hates his students.
Oh no, he is.
Yeah,
He is.
Boyka.
This is what my friend told me. He's like, the first day he showed up to class, he's like, you guys are allowed 1 cheat sheet for your midterm and your final. And then he brings a sheet of paper like this. This is 1 page. This is 2 page. 1 page. When you write your answer, explain your answer. When you write your units, you explain your units. If you try to fake the answer, I will know. Yo,
First lecture.
yo, actually, I was in Loika lecture for 10 minutes only in my life.
Yeah.
I was enrolled in his class. It was communication system 3rd year. I went and sat down. I was hungry. It was 5:20. I took out, I don't know what I was eating, maybe a cookie or something. He looks at me and he's like, next time you bring food in my class, make sure I don't see it, I don't smell it, I don't have anything to do with it. I'm like, yo, people are hungry. I had class all day. So then I went on Eurozone, I switched to the French section, and left his lecture.
Yeah.
Dead ass from
I've
there.
got him next semester, yeah, communication.
You have him?
Yeah, sadly.
May the Lord be with you, bro. I don't know.
He posts all his assignment grades publicly, and if he even suspects that you like had a solution even close to someone else's, like not like you guaranteed cheat, like if you were even close, zero automatic and no appeal, nothing. So like literally, like every assignment he posts the grades publicly. I've seen the spreadsheets that he posts. Literally, like half of them are zeros. It's fucking hilarious.
What is he
The
doing from being
TAs
an
last
absolute
year
chump?
were like undergrads, and they were new to it, and Loika was just really strict, so they were very tough on the marking for if plagiarism.
Okay.
But also he is evil. He won't tell you. He won't tell you. But if you get caught even once, none of your bonus marks apply, and he doesn't tell you until the end of the semester. Yeah.
Okay. I'll get back on topic here. This is feedback. Feedback is pretty much, you're going to learn more about it when you take control systems. In my opinion, I think control systems should have been taken before electronics too, so then you understand this better. But it's not the case, so we have to live with it. And this is usually the general equation for feedback, where this is your output over your input. It's like your gain of the circuit with your feedback. This is the gain of the feedback network, and A1 is the gain without your feedback network. So all it is sometimes you have a system, and just intuitively, you have a system that works, but you could have a better system, but that's going to cost more money to go from the ground up. So you take the system that you already have, and then you do modifications on it to make it better by spending less money. That's the whole point of feedback loops, feed forward loops, and then feedback systems, which you will learn in control systems for sure. But this is why we're doing. This is why we learn feedback. And I'm going to start straight up with an example. We have this circuit going on, and usually your feedback is from the output to ground. So if you go to the output to ground, that's your network. Like that's how I kind of train my eyes to notice the feedback network. It's just from the output to ground because the input is connected to ground. So ground to input, we have a voltage kind of sensing, current sensing. It's like you're able to communicate from the output to the input through the ground. Does that make sense? Because both the output and the input are connected to ground, so you have some sort of communication between these two. You're sending some information from the output to the input, so then you can influence the output again once it gets there. It sounds a little bit confusing, but this is what it is. I'm trying to not get into too much control systems as I do this, but give you the intuition behind it. So first off, what's very easy to do is to find your gain without the feedback network. So you're just going to ignore that. But there are different ways to ignore your feedback network when you do it. There's non-ideal way of doing it, and there's the ideal way of doing it. If I remember correctly, in the ideal way of doing it, you can kind of just remove the resistors and then ground the gate here and then move from there. In the non-ideal way, you have like a cheat sheet with like pop, 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 and you have to pick the case you're working with. Usually that's pretty simple if you have identified your feedback network correctly. Because if you identify that incorrectly, it can be very confusing to draw the feedback network in the way he wants you to draw it. So that's one thing. But this one is ideal. So we're just going to ignore that and then do finding A1 from here. Since this was an only single transistor kind of question, I just used electronics one to find the gain. And the gain is GMRD. I'm not going to go through that. It's simple. You guys know how to get there. And the second thing I need to find is I need to find K, which is the gain of the feedback network. Now remember, one thing with feedback is that the gain of your network is the opposite. So your output becomes your input, and your input becomes the output. What do I mean? Is, forget this. This output is like a source going into this network. And this is the input. This is the input going into the network, and this is the output going out of the network. So your V out here is going to be this V1 connected from here to ground, and the V2 here is the voltage of your feedback network that's going to be fed into the input again. So it's opposite. So when you're doing gain of a feedback network, make sure you're using this as your input. This becomes the input of the feedback. Okay? And when you disconnect this is a series combination right here, and then this is V2. So if you're trying to find V2 in terms of V1, voltage divider right away, R1 over R1 plus R2 times V1. And then you do V2 over V1. That's your feedback network K. It's pretty simple. Most of the time, it's very simple to find the gain of the feedback network, assuming that you know that your output is your input in this case, right? And once you have that, you pretty much have your closed feedback. So this is your closed feedback gain. All you need to do is replace in your equation here. So A1 is GMRD plus 1 plus K, which is R2 over R1 plus R2, GMRD. There's something off here. Oh, sorry. This is R2 because this voltage divider is something here. This is R2. R2, R2, 2. Okay, that's how you find your closed loop gain. Questions about this? This is a pretty simple example, but this is how it would be done. And to find the open loop gain and closed loop gains, again, you have equations on your cheat sheet. In this case, because the voltage to voltage amplifier with a voltage feedback, we're going to use these equations. And it's pretty much the same as your closed equations. What do I mean by this? Is you want to find the R input with no feedback. You want to find the R output with no feedback. And then once you have the gain of your circuit with no feedback and your K, you can replace in this equation and find your closed. So closed just means you're considering feedback. Opens means no feedback. So this, what you have to do here to find this is just like regularly what you've been learning from the core steel feedback. So that's what we'll do. To calculate R in open, so if you go over here, this is R in, all right? Kind of this arrow pointing towards the in. So here, boom. And because it's a single transistor, my way is like just like when I see a single transistor, I just go to electronics one method because I know I'm pretty fast at it. I know I can kind of, the muscle memory from the trauma will kick in for me to get the right answers right. So I'm going to give VT 1 ampere, replace this by small signal model. Notice how I always ignore RO when I do small signal model because I'm not trying to waste time. You can do it, but in this case, it would just be parallel to RD. I don't care. G is this, connected to ground. S is connected to your input, and then you just need to find VT. And when you should find VT, that's your R in open. Again, you have this, input volt Thevenin here, 1 input current, 1 ampere current. You find your R input open, and that's your R input open right there. If you want to find the closed, all you need to do is use this equation right here. So this is, what is it? 1 plus K A1. 1 plus K is your feedback network over there. A1 is GMRD right here. And this is just your R in open, which is 1 over GM. And same thing for closed. R out open and R out closed. But the output is here. So this is where you give your Thevenin, electronics 1 method, RD, and then that's your R out closed. So this is pretty much it. This is pretty much how you do that. What is that? Okay. Same thing here.
I had one question for
Yeah.
you. For the ideal case, can you go back up to the first example that you did? When we have our feedback and we're trying to find our open loop gain, what are we doing with our feedback? Are we just removing it? How do we know what we're supposed to like ground and open circuit? I don't know if you know what I mean. Like you see right here, we took out the feedback network. We replaced the gate of the MOSFET with a short circuit,
Yeah.
and then we open circuited the output.
Yeah, I kind of like to think about that logically. To be honest, like if I were to split this, it wouldn't make sense to leave a MOSFET gate just in floating. So I would ground this, and it wouldn't make sense to show this because I would disable R2.
Yeah.
So in my head, I'm like, okay, so this one has to be grounded logically, and this one has to be open circuit.
Okay.
I don't kind of follow like rules or the things the way he says it. Like I try to see what makes sense for the circuit, you know.
And
So
would that
it's-
would that change if you had like current as your output, or would that stay the
You
same?
can kind of see where the current leads, like trace the current.
Okay.
Yeah, you trace the current and then you make your decision from there. And that's what that would be my advice for it. Okay. This is an iffy example. Um, Again, you're trying to find feedback of this, but you've seen this before in like lecture 4 or something. This is the crazy equation that he derived with V-Thevenin. Um, Again, if you remember the gain of that, I think it's in your cheat sheet as well. You can directly apply it, but it's the same principle. Now I'm gonna do step by step. If I want to draw the feedback network, again, I'm gonna look at this and I'm gonna be like, here would be grounded, and here would be open circuit, right? When I draw it here, and so they would be in series from the same idea as before. Like I don't want to leave this hanging, and it doesn't make sense to short this. So that's why I draw it here, and the output is the input of my feedback. So V out equals to V1, and then the output of my feedback is taken through R2. This is my feedback voltage. I find the relationship between VF and VI, and that gives me K from a voltage divider. Same thing as I've done before. And all it is the derivation for it. Like it's simple, it's voltage divider. And if I want to find AV closed, it's just going to be the crazy equation over 1 plus the feedback network plus the crazy equation itself. That's pretty much how it is. So it's essentially finding K is very important because you're showing that's the only way that's the only way to get your closed gains equations correct is if you have your correct K. Because the open loop gains, it's pretty easy to find if you've been practicing the whole course, right? It's pretty easy to find. So he's just trying to see if you can find a K, because the way he's gonna mark these questions is he's gonna see your final answer, closed loop, final answer. And if it matches with numbers that he has, he knows you did it correctly. If it doesn't, he's gonna read your solution, and if he notices your K is wrong, he's gonna be like, well, this guy does not understand the concept of feedback. Feed forward, doesn't understand, so 0. So get your K correct. Like that's it. Because if he goes back and he corrects it, and he's like, your K is correct, but your gain is off, he's gonna be like, at least you got the K, because that's the main thing. Non-ideal feedback. Yo, okay, this is where things get heated. This is like hard. This is hard. Okay, how many pages is that? 1, 2. I'm looking all that bad. Okay, we got this. We got this.
It's in the formula sheet.
Yeah.
So it's not as bad.
Like voltage to voltage, voltage to current.
You use the same like logical reasoning as to why you short resistors.
Yeah. Most of the time, your feedback network is always open. Like you don't short it. And you do the opposite in your circuit that you don't have changed, right? If you open on one side, you're gonna short here. If you short here, you're gonna open there, right? Because the way I say, you're trying to keep the balance. This is just like wishy-washy. This is bro science. You're trying to keep the balance. That's all it is. Like I don't have an explanation for it, but it makes sense to me, and it's been working.
Write that on my panel.
What?
Bro science.
Bros. But yeah, so this is non-ideal. So you can't just poof have this disappear. So if you want to disconnect this, you have to disconnect it wisely. What do I mean by this is you have this thing going on. All right, this one you leave it open. And again, the same logic. If this is shorted, you're ignoring R2, but R2 is part of the feedback, so you can't short it. So you leave it open. Now, if you leave this open, your circuit makes no sense, so you have to short it. Does that make sense? Like, when I think about it this way, I'm like, yo, I can't make a mistake here, because like, I can't have whatever. Because if I leave this open, there's no current flowing through it, and that makes no sense. So now I have this. All I need is I need to clean up. These two, parallel. These two, what I do there? Where'd that RD come from? Yo. Oh yeah, that's a good point. Yeah, why is R1 and RD? Why is these two are in series, right? What's parallel with RD? Yeah, VDD is actually grounded. I wrote VDD here because it's AC, but VDD is grounded, so that's why it's grounded or parallel, I should say. Okay, so this is your circuit. Now you find AV open. You have one transistor. I use electronics 1 method, and you can see that it's in one line that I can get the answer here. It's not that complicated, and I'm not going to go through the math. You guys can read it and try it on your own, and then go back to see if you get the same answer, because you will have access to this. So there's that. I simplify my feedback network. I do my AC model because there's only one transistor. I do electronics 1 model method. I get my AV open. That's one part done. Same thing. Find R in open. if I go over here, you need to make sure you know where your R in and R out is. For example, this is going to be my R out here. You don't want to take it here, for example. Like make sure you set the V out, and your V in, you want to make sure it's at your input. So I'm trying to find V in here. So boom, this is the equivalent impedance that I'm trying to find. Okay, so I have input going on to the source, because if you look at the circuit here, this is the source. So input going on to the source. The gate is connected to the R1 parallel R2, and V out is connected to this R1 plus RD over parallel with RD. And again, all you need to do is you need to find out what V in, what the hell? AV open? No, sorry. Here, this one. I need to find what VT is. And electronics 1 method, just 3 lines, 1, 2, and 3. That's it. The analysis is so simple, guys. Like, it's so simple. Don't even use GM or L, just write the KVLs and KCLs. If you don't have RO, just write the equation, you will get the answer pretty simple. So R in open is 1 over GM1. Any concerns on how I got that? Okay. R out open, same business. I'm just gonna, boom, give in 1 ampere current into the circuit and then calculate VT. My input is grounded because I'm doing Thevenin. And this is open circuit. There's no current. So this is ground, this is ground, this is 0. VGS is 0, VGS is 0, boom, gone. This circuit is what's left. VT equals to 1 times that, so that's R out open. Pretty simple so far. Feedback network. Again, if you go over here, this is your feedback network. Your V out is your input of your feedback. So that's what I have. V out is the input of my feedback. At R2, that's the output of my feedback. I find the relationship, voltage divider, I get my K. I know what open is, I know what K is, so I have my closed gain. So this is my closed gain. And then same thing here. I need to calculate R in open, which I did calculate here. R out open, I did calculate. I know my K, I know my open, I put it here, and I put it here, and I'm chilling. Chances are, if he's going to ask you a question on feedback on the final exam, it's going to be a voltage. So focus on that. It's easier for him to grade a voltage feedback than it is to grade other feedback networks. So this is all for their official cookies and cram, like legal stuff. Questions about that last example we did? Yeah.
Sorry, could I just see the non-ideal open loop gain calculation
Yeah.
here?
Non-ideal open loop gain.
Yeah, no, sorry, the ideal.
Ideal. This is ideal. Open loop. This one?
Yeah. Did you include R1 or R2 or when you found your open loop gain here?
No, because it's ideal.
Oh, okay.
So it's gone completely.
So yeah, when you
That's the point of ideal. Yeah, it's gone completely.
Oh, okay.
Yep. That's the feedback here. If there's any question, we can. I was gonna take a 5-minute break anyways. Here, washroom break, cookie break, whatever. How's the session going so far? Good. Yeah. You guys seem way more like know what's going on than last year's group. Last year they were clueless. This room had 50 people in them. Like 50. I remember a picture. Like it was crazy.
I don't know what
50
it is.
people.
Our ears pretty locked in.
That's good.
I don't even think our class.
Yeah, there's not that
I don't
many
even think our
kids.
class has 50 people.
Yeah,
Wow.
Class is really tiny. It's in Henderson.
I wonder why.
The
I
only
bet you the
person
French
who-
section's full.
Momo switched their classrooms.
Oh, he did?
Yeah, we were in Samar,
Mhm.
and one of those four guys goes, I can't see the chalkboard. Not everybody can see the chalkboard, so I have to switch. Then we ended up in Henderson with the columns block the fucking chalkboard.
He is like that. That's so funny.
He needs his chalkboard.
You know what people did last year on their final?
No.
For non-ideal. And then
They
you
were,
have
were
like
they confident at least going into it?
Oh, you're asking like what they got in their finals?
No, I mean like the people who did it last year, like how, like were they confident going into the exam? Because they said there were so many people.
Oh no, they came in.
Yeah.
Okay, it's gonna sound so bad. They came in. They didn't have any idea, bro. They didn't know what Cascode was.
but like in what
They didn't know what Cascode was. Like I found myself having, like you know how I breezed through the first? That was like my first 2 hours of the cookies and cram. And the rest, it was 5 hours. The next 5 hours were like teaching this shit.
If you actually
And then they left. They're like, oh wait, can we have these notes? I'm like, them people didn't put in any work and they're trying to get a free notes like this, so I made them pay.
In the breadboard and just leaving the other end.
Yo, I made $250 that day.
So it just goes by.
$20 for people. No, but this time I'm giving it for free. Like I don't care.
You already know there's zero current, so regardless, it's always gonna be grounded.
But they had no clue.
I would always
Clueless.
think about that as
One of them kids, he sat in the front row.
what would happen to
Like
people
I was in front of a boy. He was like here,
you would
and he
just
asked,
stick a resistor in your
"Excuse me." I'm like, "Yeah." He
There's
said,
no current that can go.
what really is gain? I'm like, yo, this is electronics 2G. What are you asking me what gain is?
That's crazy.
And he's in my year too, which is crazy.
Yeah, he's had some crash outs this year.
No, he's okay. This in my opto class. In my opto class, he like, prof is like the TA is saying like, yo, we have an angle of pi by 2 radians. It raises him. I'm like, okay, what are you about to ask now?
Oh no. Oh
It's like-
no.
What's a radian?
Oh my.
Is that like a fourth year course?
Yes,
How do you
sir.
get that far without knowing?
I do not know, bro. I don't know if
Yeah.
he's trolling, but like, I don't think he was trolling. Like the way he asked, he was serious. He was like, what is it? You know, like he was intellectually like intrigued. Like he wanted to know what a radian was.
AI is a powerful thing, man.
Man, it is a
People like
powerful-
that can get all the way to the end.
According to Schreimer, a radian isn't even a unit.
That's true. Yeah.
It's not a unit,
So apparently it's not a unit.
but Schreimer, you know, he has opinions.
Yeah.
Yes.
Yeah. a lot of
Schreimer
it-
has opinions. Have you seen his Twitter?
Yes.
Yeah, he has opinions.
He also has some pretty hefty PhDs. So
PhDs.
yeah,
He doesn't have one PhD.
he's two PhDs.
He has two
One in
PhDs.
physics, one in math.
Why is he teaching ELG
I
for
don't
then?
know. That's why we're all wondering.
In the first lecture, he said, guys,
I'm not an actual
technically,
engineer.
I have to disclose this. I'm not an actual engineer, so I can't give you actual engineering advice. But
But I'm gonna spend the last course on P Eng. Go through the ethics of being an
But
engineer.
my, but this is my company.
Yeah.
Who wants to make some
I mean, his class now makes so much more sense. So it's all derivations
Yeah.
and stuff instead of something like
Yeah.
problem solving.
He's doing the optics and electrical engineering course next semester. I'm taking that.
Oh yeah.
That'll be interesting.
I feel like that would be a good Shriner course. Though.
Yeah.
Like he's that type of person.
All projects.
He's a good yapper. He yaps about
Dude, he loves his master students so much.
Yeah, he hates
kept
undergrad.
talking about them.
Hates undergrad with a passion.
He's a lot. He also hates his own grad students. Like in class, he's like, my grad students, I need more of them. Like they're not that good.
He hates entire countries, so I wouldn't be surprised.
No boy. Oh
I
man.
wouldn't be
Dude,
surprised.
someone I know got blocked it on his Twitter.
Getting blocked from Schreiber is
Yo, is he having this bandana phase still?
no.
Dude, he
Okay.
had his whole cane
He
phase,
had a
and then he
cane
moved
phase.
it to bandana.
He's back to the cane.
Back to the
Knock your
cane
house.
phase.
He was cane back in my day too. Like, and then last year he was bandana, and now he's back to the cane. But he had no beard with us.
Oh
The beard,
no.
he had no beard.
I
He was-
can't imagine him.
That's the videos that
He looks so weird.
Oh, he would look.
Yeah.
The beard kind of, nah, bro. I can't be saying shit like this, bro.
He,
I was
he
gonna-
actually looks pretty good with a beard. I can't lie.
Dude, you're the biggest
No,
Shriner
no, no,
boy.
no, no,
This
no.
guy's the biggest Shriner.
What'd you say?
He looks pretty good with a beard. I'm telling you, bro.
Yo, G.
Listen. Without a beard, he has all the wrinkles and old beards, bro. He looks.
Hey, I'm not trying to go back to edit this video or trying to find where crazy stuff was said and then cut it out.
AI generated.
It's happening. It's just. It is what it is.
It is what it is. It's not gonna be posted on IEEE's channel. It's my channel, so I guess it's just like I'm doing IEEE a service. Like, yo, don't flame me. Someone reported me last year, bro,
You for what?
for my own videos.
For what?
Yeah. You know, I made a joke in one of my videos. Like, I was like, my
You're gonna have to cut it out of this.
I don't care.
Say it.
I don't care. I'm rage baiting right now, bro. I don't care. Yeah, it was Electronic Swan. I said like, oh, by the way, I checked my stats. My viewers are 100% male. I want to keep it this way, so let's stay locked in. Someone took this, screen recorded my video. This is my channel, by the way. Sent it to IEEE chair.
No.
Yeah. I had to have a meeting during my lunch at my co-op with Equity. Like I usually know you.
So what was this about,
I'm like,
holy males?
damn. It's a joke, bro. Like it's a joke, G. Like, I'm like,
Those are
the-
like the
oh,
degens in their class all.
no, there's a dislike in that video. I have one dislike there.
Oh.
Yeah, the dislike is still there. The dislike. I'm like, yo, okay, okay. You're clearly benefiting from it, but okay. All right. So this is academic rogueness. Um, yes. So this is probably very important exam kind of question that you need to focus on a lot. This is VCC. These are the topologies, and the way to make this question easier is to look at your circuit in stages. Do you remember? Has Momo in class ever said, if you try to find the gain of the overall circuit in one equation, it's going to be very, 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 very difficult. Try to find common point. Vx something. So this is one of what he means by here. So you have one amplifier, a second amplifier, and a third amplifier. So you need to see it in three stages. This stage one, this stage two, this stage three. So first off, we're going to treat this as ideal, meaning that when you disable your feedback network, you have no feedback at all when you're doing open. So AV closed is this equation. So we're trying to find AV open. Again, look. This is actually pretty simple. So once we disconnect the feedback network, this is your feedback. Okay, this is the feedback, and then this is your degeneration resistance RS at the emitter of the third transistor.
Why wouldn't RS be included
In the feedback?
in the feedback network? Yeah.
Yeah, that's one thing. And the second thing is, like
On
you,
the green.
that too, but also like some transistors you have a degeneration resistance RS. There's also one clue is
It's for the-
feedback is given with numbers,
Okay.
and then non-feedback is given with alphabet.
It's for the MOSFET, right?
Yeah,
RS.
yeah, pretty much. It's associated with this transistor. Like it's something to do with this.
Okay.
Was that how it's labeled on the exam, like R1 or 2 and
Yeah,
RS?
yeah, yeah.
Oh, so you just know
So
right away.
you just know if you're smart, you can like,
Yeah.
okay, I see what you're doing. Thank you, Momo. But that's the French cross doing.
This is fried, by the way. This question looks fucked.
It's okay. We'll try to break it down. This is the last thing. We'll take some time here. We're not going to go too serious. So if I'm trying to find, again, remember we're turning this at ideal. This is the equation. I'm not going to explain that again. We're trying to find AV open. So we disable a feedback network. Again, if this is my feedback, here, what's going to happen? Ground, because I can't leave this floating. And for the feedback itself, what's going to be here? Open, right? Something like that. There we go. So I have this. Boom, the feedback is gone. This is grounded. RS is still here. Now, if I want to find AV open, what am I trying to find? I'm trying to find V out over V in, right? Where V in is VS in this case. So V out over VS. So now I want you to imagine three amplifier questions in one question. So this is amplifier number one, amplifier number two, amplifier number three. Okay, so three stages. This is the output amplifier number one. I'm going to call it VX1. This output amplifier number two, VX2, and output of amplifier number three is just VO here. Okay? So there's that. So V out over VS, I can write it as the gain of this amplifier, which is VX1 over VS. That's your first stage gain. What's the gain of stage two? VX2 over VX1. So that's stage two gain. What's gain of the stage three? V out over VX2. Okay? But now look at what happens here. You have VX1 cancels VX1, VX2 cancels VX2, and what's left? V out over VS. So you have your open gain. But you're not just like crazy raw dogging this thing to get the gain. You're like, I'm gonna do this, then I'm gonna do that, then I'm gonna do this. But now, if you look at this and you remember all the gain equations from electronics 1, you look at this, you're like, okay, input is given to the gate, output is taken to the drain, so this is a common source. So if I know the gain already, I can replace it by the gain equation. Exactly, GMRD, you have it. What is it? It's the same. It's the same thing. So it's gonna be here. And what is this? Is it different? It's different because this one output is taken at the source. So then I actually don't know, but like if you have it memorized, you can put it here. So you see how quick you can get that gain. We're cooking here. We're cooking.
When you took the class, did Momo give you marks for that?
For what?
For like if you
100%. 100% he has to.
Has yelled at us several times about he's not going to do that.
You have to prove it.
He goes, if it's not on the cheat sheet, you have to prove it. He said that 100 times in the class.
Well, that's he said that for the equivalent resistance, but he said like you should memorize like the common gains because you can write the common gain, but if there's like a resistor, I think this is still normal, but if there's like a resistor at the source,
Then you gotta know.
I'm sure if you write like common source gain.
Yeah, if you show him, you know what this is. Don't just write GMRD. Be like, okay, this is common source, and gain of common source is that. Yeah. You see, so this is how you do it. This is the stages. Again, if you don't know, have it memorized, you can derive them, and it's not that bad, I think. Oh, I actually have the numbers too. I actually have the number. Again, don't go based off the numbers. Try to know how to get there, because he might change his stuff.
Yeah.
And like if you guys write this, and here's the numbers from last year,
Oh, you're cooked.
I'm cooked, and y'all are cooked, and I'm going down, taking everyone with me. Okay. Okay. So this is how you find the gain of stage one. Electronics one method, you find it is minus GMRD, like you said. You can just write it away. Stage two, it's the same as stage one. So this is the answer. Stage three. Now, if you have a follower, what's the gain of a follower? This is a follower. So you know the gain of this, this one you can just legit be like, yo, this is one. Yeah, but you could also say this is a source follower.
Yeah.
And then a follower has a gain of one.
If you're running out of time, that's a good.
Yeah, that's a good way to do it. But if you look at it, it's 4 out of 5. 4 out of 5 is the same as 5 out of 5. Like I don't care. Like this like what difference does it
Just
make?
make one of the garbage assumptions.
Yeah, exactly. No. That's all it is. It's like GM is greater than this thing. Yeah. Look, if this is way bigger than this, so if you ignore this, it's GM over GM. It's 1.
Yep.
It is 1. Like 4 out of 5 is 1. But this is AV open gain. So that's how I find the AV open gain. But now you want to find the feedback, the gain of the feedback network. Again, your output of the amplifier is the input of the feedback. I'll repeat it in this so you can hear me during the exam. Not forget. This is voltage divider. K is 1 over 10. Okay? Not going to go over that. We've done that 3 times now. And AV closed, easy. You have open, you have K, easy. What was AV open? Look at the difference. Difference is wild. Make sure you say volts per volts, so he knows you're talking about a voltage amplifier and voltage feedback. So write volts per volts, even though volts per volts is 1, but you read that. So now you want to find R out closed. Is it R out closed or R in closed? R out open. Holy cow! Where's R in? Do we not need R in? Did I skip R in? Okay, closed loop gain 2.1. All right, we're doing R out closed. So we're trying to find R out here, but it's pretty simple. We're gonna use the same method. I'm gonna try to find the output impedance of this amplifier. I'm gonna try to find output impedance of this amplifier, and then I'll try to find output impedance of this amplifier. Why I start with this is because if I find RQ1, the output impedance of this amplifier is a resistor, right? And then we have a resistor here, and I can use the same thing, output impedance, like use my cheat sheet to find this resistor, and then I'm kind of like just like coming to or out. Yeah.
Doesn't it all just get shorted?
It will get shorted. You can straight up say that. You can straight up say that, but I prove it. Because disable independent sources. So then 0, 0, 0, 0, RD1, boom. Now this is RD1. So RD1. Now you find RQ2. So finding RQ2. There's no current here. So 0, 0, 0, this RD2. It's easy to prove. It's easy to prove. There's no equation written here. And it's in stage 3. You have RD2 here. And now you're trying to find R out. So now you do a little bit of math. RD2 is connected to ground. This is the gate right here. The source is connected to VThevenin given 1 ampere current. And the drain is connected to ground. Okay. So now you do a little bit of math. I started with a KCL at this point because you have this current is equal to 1 plus Vt minus 0 over Rs. So this current here, GM-VGS, plus one input current that I gave equals to Vt minus 0 over Rs, the current going through here. And if you look at VGS, VGS is gain minus source, but the source is connected to Vt. So the source is Vt, and the gain is 0, the gate is 0. So VGS is Vg minus Vs, Vs is Vt, this is 0, so VGS is equal to minus Vt. So GM-VGS is equal to minus GM-VT. So this I replace by that right here. Now I have Vt in one equation, isolate for Vt, and I have my R out closed. Pretty simple, pretty simple. It's just that. If you follow like the stage 1, stage 2, stage 3 kind of situation, you will get there pretty quick. So this is R out open, and to find R out closed, you just do the equation. You know what K is? You know what R out open is? Don't be like me, because I use R out open here sometimes. Like this is gain, this is AV open. So you put that here, and then you get your R out closed. And usually your R out closed is a very small number. Your R in is a very big number. So if you get like something like 2K, you did something off. And what's the next part? Okay, so this is non-ideal now. Oh Lord.
Non-ideal.
Yeah, so you did it ideal, and now you're gonna do non-ideal. It's the same thing though. It's the same thing. But it matters how you disconnect your feedback. Again, for the feedback, it's gonna be open. For the circuit, it's gonna be shorted. It's the same concept as before. Same thing here. And then when you clean things up, you're gonna have R1 parallel with R2 here, and R1 plus R2 parallel with RS. Why is it parallel with RS? It's because it's for the same reason as before. R1 plus R2 parallel with RD. The feedback network gain remains the same because it's still R1, R2, and your output is still the input of your feedback. This equation stays the same, but you need to find these gains again. Stage 1 gain will change because of that, potentially. But I don't know that. I'm not sure myself. And then what did I write here? Stage 1 gain. Stage 2 gain experiences no change from above, stays the same. Okay? And stage 3 gain, we'll see. But I think I calculated it anyways. Okay, yeah. So what was VX1 earlier? Like the first gain? It was minus 40? Yeah. So this was the previous gain. Minus 40. And then this is the current gain now. So what is that? 500 over 17. So it's like 30. So it went from 40 to 30. So that's how you know you're on the right track. Like with feedback, you know, you can kind of get a closer value. But I just calculate the gain of the first stage. So this one, I do that, I get my gain. Stage 2 is gonna experience no change. So I'm not gonna calculate the gain. I'm gonna use the same expression minus 40. And stage 3, again, it's a follower. So it's still gonna be equal to 1. A follower's gain is equal to 1. 2 out of 3 is the same as 3 out of 3. Yeah. You can just write it there. It doesn't change much. But then you do the first stage times the second stage times the third stage, and then you get your AV open here. And AV close is AV open over 1 plus K AV open, and then you get 9.87. This is your AV close gain. And what is that? Oh, this is finding the output impedance close of non-ideal. So you see how long that question is? But if you...
Does he ask you both, ideal and non-ideal?
Yeah. That was the question. That's the question. That's the question. Yeah.
Isn't it like for you just like reuse what you have for ideal, but you plug in your new resistances?
Yeah. There we go.
He's trying really hard to mess you up.
I started with that question when I was in my final.
Okay.
I started with that one. I was like, yo, it's like I started with the question worth the most when I'm most fresh in my head.
Yeah.
So there's this. I found RQ1. Same method as before, to be honest. Like exactly the same method. What is that? Resistance per GM definitely not zero. Oh, okay. Oh, I see. Yeah, it's the same thing as before. So RQ1 equals to RD1. And then you find RQ2, and then, you find R out completely. Same method, same step-by-step process, but you're just doing it now with non-ideal, and you consider these resistances. Same topology as before. Previous expression can now be modified. So, like, exactly, yeah? R out is RS parallel with 1 over GM, but RS is not RS anymore. It's R1 plus R2 parallel with RS, because you're considering the non-ideal feedback. and then you use your equation. So this is your R out open, and then your R out close is this. Yeah, so it's still a pretty small value. That's how you know you did it right. And this is this question. But this is how it's done. Um, it's correct.
I'm not saying that it's gonna take a long.
Yeah. What, doing this?
Yeah.
Yeah, just practice it. That's why I said it's just like if you know the games of the stages,
What,
you're saving time.
what would he change? You know.
I think he could ask you for R in as opposed to R out, something like that.
Do you think it's possible he could like switch this to BJT, or is that too difficult?
Yes.
He could. No, he could actually change it to a BGT. Yes.
If he asked us for RN, it would just be infinity.
He could. You know what he could do as well? He could do
Not-
BGT MOSFET.
Oh yeah, it would just be the same R out. Yeah.
You know?
But then your game would be different, no? Like, can you still do like the BX1, BX2 method?
Yes, 100%. You can.
But since there's current going into the other MOSFET, like, how does that change things if we find that? Or
If you find the ratios is going to take care of it for you.
Yeah.
Yeah, the ratios will take care of it for you.
But like, if we're finding the game, like when we're finding the game of the MOSFET, it's good because there's no current going into the other MOSFET. It's just a simple GMRD. But if we're doing a BJT, we have to do analysis of like the whole thing, no?
Yeah.
It would be
So
a lot more
if you do
Because like,
BJT, it's
you'll have
basically
current
RN
going
is
from
complicated.
you'll have current going from stage 1 to stage 2, which means you have to keep into account stage 2 when you find the game for stage 1.
You'd have to do like equivalent resistances on each of them
Uh,
to simplify to one.
I don't think so. Because like the gain of the first is just the voltage over the voltage.
But like the voltage changes when you have a BJT because you have current leaking into the stage 2, which it's like you're having the stage 2 resistance in parallel.
I see. Yeah, in that case, yeah, for sure.
Do you think it's probable he do something like that drastic?
No.
No.
Because like all the examples you've done are MOSFET, is that like typically what he works with?
But then you could do GMR out.
Yeah.
You do equivalent impedance of
Yeah,
this,
yeah.
equivalent impedance of this, and then
It just makes it longer.
yeah. So it's like use your weapons, like whatever you have.
We pissed them off too much this year, bro. We might-
I don't think no. I think this
I
is.
think he already wrote the final and like has it set.
But yeah, this is pretty much what I have for you guys today. The this document, this one will be posted today on the ELG channel, like on Discord. So you can look over that, and then
Put the wrong one.
the wrong one actually, I need to send it for you guys to check if it's correct. So I don't know, I'll send it to you or I send it to David, and then you guys can check and then get back to me about the mistakes that I've done. Sounds good? Okay. I hope the guys on Zoom don't have any questions here.
What do you think the difference is between, this is a voltage, if it was like current voltage or current.
Just the way you connect your feedback.
Yeah?
Yeah, you have to use your cheat sheet.
So like this one,
I don't have the cheat sheet. My electronics is closed. Momo closed it.
Where's the
Current
Does
is
anyone here in
open.
the French
Do you know?
section?
You know what we noticed he did during the midterm?
What do you do?
He closed the class during the midterm. Because I guess he was like thinking someone would be going in the bathroom with their phone or something like that. We got out of the class, went to check our grades, and it was like the class is closed.
Oh my.
And then it reopened like an hour later. And it was like, what the heck?
I thought I got in trouble for like cheating or some shit, and that it just closed for me specifically. I got so worried. I emailed him. I'm like, hey, the class is closed. I want to work on this assignment. Could you open it up?
Oh, sorry, I forgot.
Yeah. I was stressing out.
Yeah, man. Yeah, this is it, boys. Hey.
I think the most stressful part of this exam is when you're about to take your seat and Momo just starts yelling at you like, sit where you see your exam paper. Because during the midterm, he was like yelling in people's faces to sit at a paper.
Yo, remember funny stories? Like when I was writing electronics 2 final, I have a friend. He was sitting in the corner, and you know how he's like, smartphone, smart devices, smartwatches in general are not allowed. Smart devices are not allowed. So my friend, he forgot to take off his Apple Watch, and he's writing the final. He's writing the final, and he raised his hand to go to the washroom, and it was Momo there, besides him, and Momo was like, smartwatch, yo, I'm hearing this. He's like, he's right there. I'm hearing all this shit. I'm like, yo, bro, what did you do? And he starts like, Professor, I am so sorry. I have a serious heart problem. I need to monitor my heart rate. I'm so sorry. And then Momo was like, okay. And he's like, yeah, no. I need to monitor my. Actually, I need to go to the washroom to see if everything is okay with me. Blah blah blah. And he's like, okay, go to the washroom. So he goes to the washroom, comes back. Momo comes with him with a sheet of paper. It's like, okay, file, right here, what's your condition? Why'd you had why you had your freaking smartwatch on you? And then that's it. He never got in trouble. Bro, that guy does not have a heart problem. He runs 10K in 37 minutes. He does not have a heart problem. The way he pulled that up, I thought he was crying. Like I was like, yo, he should be given bonus point for this acting. How do you escape? How do you escape Momo? How did Momo let him pass like that,
He's in the
bro?
wrong field, bro. If you get into acting,
Yo,
you're
I
bad.
swear.
That's the greatest
And me, I'm just trying my hardest not to laugh. You know Tristan?
Yeah.
He's Tristan,
Oh,
bro.
it was
He's Tristan. You know Tristan. It's Tristan.
Yo.
And then, like,
Dude, Tristan's crazy. I remember the modern control.
Yeah.
He tried to sit beside X because he didn't study at all, and it was assigned seating. And then someone came up and was like, "Oh, I think that's my spot." Tristan's like, "No, I think it's mine." And as the dude goes back to check if it's his spot, Tristan just walks away.
Your K equation will change.
Okay, so I dropped names on the video too. Sorry,
I feel
Tristan.
like we should stop recording.
We should stop recording. Yeah, for legal. Yo, my mouse ain't working. My mouse is stuck on the iPad.
Oh, you probably have to shit like.
Yeah, it's not. It's not. Okay, let me
If
just.
you were to compare like the electronic, say